Hi, welcome to the OpenACC workshop presented by the NSF XSEDE program. This was originally a one-day hands-on event that you can view at your own pace. If you look at the link below, you can get access to the content and slides used by the original students.
So, OpenMP 4.5. As I mentioned to you early on, the idea with OpenACC was the OpenMP committee spun it off as a quickly evolving, something that can evolve flexibly and nimbly, while OpenMPC, which is a mature spec, didn't have to worry about meeting every 6 months to improve the spec or whatever. Well, things improve. The idea being that they'd merge back together around OpenMP 4, and they're up to now 4.5. That didn't happen for reasons I'll explain that are slightly inconvenient for those of us in the community. So the idea is, well, we can skip this. This is the important part here, is that OpenMP and OpenACC look very, very similar from a directive approach because, again, they come from the same background, they're using directives. The difference is that OpenMP was developed for multi-core shared memory machines. It was developed to program multiple cores, like we do in OpenACC, but that always share memory. There's no data management, no data movement. Up until accelerators came along, all of your memory was sitting there accessible by your processors. If it wasn't, used MPI on a totally different type of machine. But this idea of moving data back and forth across a bus was new. That's what OpenACC was built to address. OpenMP doesn't have any of that. So OpenMP also, though, was built around a world that assumed that your cores were not our simple-minded GPU cores that can only do a little bit of math and they're kind of slaved together in groups and they have this weird hierarchy. No, an OpenMP core is an actual bona fide regular processor. It's like an Intel processor. And you don't have thousands of them, you have 4 of them maybe as a common case. But they're independent, they can do their own thing and they share this memory. So they are meant to address different problems. OpenMP, because of that, has a whole lot more flexibility and complexity in what a given core can do and the way a task can operate. It also assumes you as a programmer are taking much more responsibility for that stuff. So, for example, in OpenMP, when you put parallel 4 in front of a loop, OpenMP will always parallelize that loop. It assumes you know what you're doing and that you're worried about dependencies and everything else. It's not like OpenACC that will say, sorry, you're screwing up, I can't parallelize this loop, go back and look at it again. OpenMP does the opposite. It always assumes you know what you're doing. So there are different approaches for reasons that make sense from the backgrounds they come from. Now, what has caused the original merging of these two to not happen is along the way, Intel decided that accelerator programming was also very important and decided that, like in the past, anytime they're threatened by new technology, they say, how can we do this with what we do, which is Intel chips? And so they said, we're not good at building thousands of simple cores like the video game people are, but we are good at building sophisticated cores. Maybe if instead of having thousands of them, maybe if we could do dozens of them, that might be a good compromise. People might like that. Let's make a chip that has 60 cores on it. Instead of 3,000, we'll have 60, but those 60 cores will be more powerful. They'll be actual real processors. And that is Intel's many integrated core or mic approach that turned into the first generation, which was the Xeon Phi, Knight's Corner, and that is the one that is currently in Stampede machines owned by XSEDE, so the XSEDE Stampede machine. And it looks like, so here's a picture of the card. Whoops. It's actually a single chip, but that actually is the picture of the chip right there. So it's a single chip that has 60 cores on it, Intel cores, goes on a card that you plug in, looks like a video card kind of. Those cores, though, are a little bit different than people think that they're like Pentium cores from the 90s or something. They're not. They're really modernized to give you better math operations. So they have very wide vector registers to give you good floating point operation, and they have so they're not Pentium chips. The way they were organized was a ring bus connecting them all together with some memory attached to the bus too. However, the latest version of it, the one that people are more excited about because it's newer, is Knight's Landing. Knight's Landing is laid out as an array instead of a ring bus. It's an array. It's got up to 16 gigabytes of memory. It looks a little bit more like this from a high level. It has on the board, it has the 60 cores here in a grid. It has some very high bandwidth memory like a GPU has on board, but like a GPU, not a ton of it, only however many gigabytes. Then it has a bunch of regular memory chips, your DIMM chips that you buy, when you boost up your desktop type machine. It has hundreds of gigabytes maybe hanging out here. That's what a modern Knight's Landing looks like. So comparison between these looks like this. It looks like basically you've got on a CPU a small number of cores, typically programmed with OpenMP, and they have a large amount of memory. You might have hundreds of gigabytes of memory, and a decent sized cache actually on them. A GPU, like we've been using today, has many cores, which is actually thousands of them. It has a tiny amount of cache memory on them, the things that we've been talking about, the cache that we actually just briefly mentioned. But it has very high bandwidth memory, so it gets very high bandwidth. Many integrated cores kind of in between the two. It has maybe 60 cores. It does have 60 cores. There aren't a lot of variations of it. It has, however, both high bandwidth memory and regular memory on board. So it's kind of a hybrid machine. So OpenMP needed to roll in data migration. It needed to accommodate the fact that we do have to move stuff across this PCI bus. It's not all shared memory. So OpenMP 4 rolled in as an instruction something that looks like OpenACC, the target command, target device, along with mapping. And so I put a nice head-to-head chart here so you can see how easy it is to go between the two. In OpenMP, we have something called target data that does the same as data. We have target enter data that's the same as enter data. Target exit data, the same as exit data. Target update, the same as update. So you can see the commands are very, very similar. The data clauses are also similar, except with just, for whatever reason, different names. We have map in, map out, map in out. It's a version of copy, copy in, copy out, copy. We also have create, it's called alloc. A couple of things we didn't look into for dynamic allocation. We can delete things on the card, and we can delete them forever, release and delete. So we have very, very similar clauses between the two. The compute constructs start to look a little bit different, though, because, as I mentioned, the others are just concerned with moving data back and forth. You'd imagine they look very similar. Compute constructs reflect the fact that things are a little bit different behind the scenes. So whereas we have our parallel regions in our kernels, instead here we have parallel and for do. So things are pretty similar, but a little bit different. There are a few things that are outright different here, which is that in OpenMP we have much more sophisticated threading control because OpenMP is built to deal with the fact that a core is really its complex own device living in its own space. So we have very sophisticated commands to do things like tasks with dependencies. So every single core in an OpenMP program can be off doing a totally different thing, whereas we can see with GPUs that's not the case. So they're very similar, though, and if you're writing code today and you wonder which one you should use, I give you a few slides here. I'll just pick one of them out for the sake of time to show you the differences. If you're writing OpenMP 4 on a Xeon Phi, it's pretty straightforward to parallelize a loop. It looks like this. If you're using OpenMP 4 on an NVIDIA GPU, it's a little bit more complicated. On the other hand, if you're using OpenACC on a NVIDIA GPU, it's very, very simple with kernels command. So if you put enough of these examples together, and I have a few here that you can stare at, you might come to the conclusion that it looks like NVIDIA, in particular, has really done a good job of making sure OpenACC works really well on NVIDIA stuff, and Intel has done a good job of making sure that OpenMP 4 works really well on Xeon products, Xeon Phi, and the Knights Landing and Knights Corner products. And you would be right. As a matter of fact, it reflects the harsh reality that the two commercial entities behind the scenes that had a lot of power, NVIDIA and Intel, have kind of been pulling the spec apart, keeping that merger from happening so that they could really support their own devices best. So at this point in time, if you're going to use NVIDIA GPUs, you probably should be using OpenACC and an OpenACC compiler. If you're going to be using Xeon Phi, you should probably be using Intel's, you don't really have much of a choice, Intel's compiler with the OpenMP 4 stuff. GCC also supports some of that, though, but you'd be crazy not to use Intel to support that. However, switching back and forth between the two is more an editing exercise than it is rewriting your algorithms. So whichever hardware you're using today, I would suggest that that's the approach that you use. And if you have to port your stuff, you're not going to be kicking yourself because you've committed all this effort to changing the algorithms. It's more an editing exercise. As a matter of fact, a few people have written some editing tools to try to automatically convert between the two. The future for both of these companies, they hope that Intel hopes that you go hostless and just buy a bunch of Knights Landing and stick them in a room in racks of Knights Landing and don't need anything else. NVIDIA would like you to buy just racks of GPUs with some simple-minded core on board that just takes care of the serial part of the program, something like Project Denver they have going on. So that's the future as they see it. Here are some things, the very last thing I want to cram in here before they cut us off. Here's some things we didn't cover today. OpenCL. OpenCL is kind of the open version of CUDA. So it's low level, but it gives an alternative to proprietary CUDA. CUDA is an NVIDIA product, and it works on NVIDIA stuff only. So OpenCL was an alternative. It's supported by everybody, including NVIDIA and Intel and AMD. However, it has lost most of its corporate support because Intel is now supporting OpenMP as the way to program their devices. NVIDIA, of course, would prefer that you use CUDA or OpenACC to program their GPUs. And AMD, who was the last player in the game that was really a big fan of OpenCL because it kept them relevant in this stuff, they've now got a fusion architecture that uses a different approach. They don't really care about OpenCL. Unfortunately, OpenCL is the kind of thing that has to have vendor support. This is fast-moving hardware that needs device driver level support. If they don't have that kind of industrial support, they can't keep up with the other players in the game. So OpenCL is lost momentum. It's the most optimistic way I think I can put it. Let's see, what else is there? Fortran 2008 has threads, and C11 has threads. Python has fake threads. They don't actually do anything to the global interpreter log. So there are some other ways to do threaded programming. None of these at the moment apply directly to accelerators or GPUs. These are more interesting if you're doing multi-core kind of stuff. The OpenCL stuff's the only stuff that works well on GPUs, but like I said, I'd be hard-pressed to suggest you invest time in something that is becoming less relevant by the year. I will entertain questions.